We are trying to solve for the melting point. Are we trying to get the exact melting point? We just want the higher number. Okay, so really what we're solving for is which one is higher. So this is asking a ranking question. To have a higher melting point, what does that mean?
To have more forces.
The individual molecules have a stronger force between them, which means I have to put in more energy to cause them to break away from each other. That's why I have a higher melting point. So a higher melting point means a stronger force. Okay? So really what this question is now asking is really which of those two compounds has the stronger force? Okay? Well, to determine the force, let's take a step back from that. Do either of those say what the force is? No. So what we have to be able to do is interpret what's written there to achieve a force. Right? And what we talked about on the previous slides with our intermolecular forces is that those forces come from the bonds that make up those molecules. So what we need to go through and do for each of these compounds is identify the bonds that are present. So what bonds are present in 1A? London dispersion is not a bond, and I'm trying to get more specific. I want to know the specific bond. And if you're looking anywhere other than literally the structure 1A, you're looking in the wrong place to answer the question. Polar covalent is not specific enough. I want to know the specific bond present in that compound.
Carbon to hydrogen.
Carbon to hydrogen is an awesome, valid answer. There is a carbon to hydrogen bond in that structure. Are there any other bonds in that structure? Typically, we get a shout out that it's no, because we see carbon to hydrogen, we see hydrogen to carbon, we see carbon to hydrogen, hydrogen, right? So we say they're all carbon to hydrogen. Let's start drawing our first carbon. We know it has 3 hydrogens connected to it. How many electrons should carbon have around it? 8. It needs to have an octet. Goes all the way back to Lewis structure, which means I know there's a missing bond. What is that missing bond to? The next carbon. That next carbon has what things connected to it? It has 2 hydrogens because it says CH2. How many electrons around that carbon is drawn? 6. How many does it need? 8, which means there's a missing bond. What is that bond to? The last carbon. What's connected to that last carbon? 3 hydrogens. How do we go from that formula to that Lewis structure? Some of that is a bit of practice. Some of that is interpretation of that formula. Right? That formula could be written in a very awful fashion. It could get written C3H8. Right? In that case, we don't know what the connectivity is, which atoms bonded to what, and it becomes more confusing to deal with. Right? That's why they wrote it out in what is known as a structural formula. They're trying to show the individual connectivity between the atoms so that we know it moves in sequence from left to right. Why left to right?
So that's how you write it? Or how you do this?
That's how we read in the US, right? We read left to right. That's why the formula is established that way. Okay? Now that we have a structure, it becomes much more apparent the bonds that are present. We have the carbon to hydrogen and, as was shouted out, we have a carbon to carbon. What kind of bond is a carbon to carbon bond? That is a non-polar covalent bond. How do I know it's non-polar covalent? It's same atom to same atom. That is the definition for our non-polar covalent bond. Carbon to hydrogen, what kind of bond is that? A non-polar covalent. How do I know that? That is the definition for non-polar covalent. Right? Those slides that we went through and we talked about what each of those pieces of information were, you have to know that information to answer this question. So it's what is the fact, you have to know it, and now you have to apply it. Okay? This is the application part. At no point will you see a question, what is the force? You have to apply it out. If you have a nonpolar covalent bond, what type of force does that lead to? The what? I'll accept that. Our London dispersion force, we'll get back to the other part of that starting. The nonpolar covalent for carbon to hydrogen is also London dispersion force. Okay. What are we looking for here? Go all the way back to what we said. Higher melting point meant stronger force. So if LDF are our two answers for 1A, what might we already start to do? They assume the other one's correct. Why? LDF are the weakest forces. So we might start to make assumptions. Before we make assumptions, because I don't like looking like a donkey more than twice, we need to go through and look at the other structure too. What bonds are present in 1B? Carbon to hydrogen. Fantastic. What else? Carbon to carbon. What else? Shaking your head's a good answer. There isn't any other bonds. That's it. Okay, what kind of bond is a carbon to carbon? Nonpolar covalent. What kind of bond is carbon to hydrogen? Nonpolar covalent. What kind of force comes from a nonpolar covalent bond? A London dispersion force. What kind of force comes from a what kind of force comes from a nonpolar covalent bond? A London dispersion force. Which of those is the stronger force? What's that? Neither. They're both London dispersion, that's it. So now I compare across to find the stronger force. Which force is stronger? London dispersion or London dispersion? Neither. Damn it. How do I know which one has a higher melting point? Well, maybe they have the same melting point. Are those structures the different or same? How do you know they're different? There's more stuff. So should we expect their melting points to be different? Probably. Okay. How do we tell the difference between their melting points then? They have the same number of forces or same strength of forces. What determines our higher melting point? Stronger force. So is referencing the bond necessarily useful? No. How many of you can break a piece of dry spaghetti? Okay, 3 or 4 of you, good. Okay, presumably the rest of you could too. You just haven't tried to break spaghetti. It's not that hard. You just snap it. Okay. How many of you have taken a bag of spaghetti, pulled out the entire thing of spaghetti, and tried to break that? Okay. How many people can do that? Okay. Make it 4 bags of spaghetti. Okay. Why is it now becoming harder? There's more individual spaghetti pieces to go through and break. There's more interactions that you have to snap. What's changing as we go from 1A to 1B? Not quite more reaction. Yes, there's more bonds. If there's more bonds, what does that also mean? There's more London dispersion forces. There's a larger surface area for that larger molecule, which means there's more contact points where London dispersion forces can come into effect. So when we're looking at our melting points, it's not just the stronger force, it's also the amount of force present. Is that amount of force harder to interpret? So everyone say, yeah, that's not harder to interpret, that's totally easy, I understand what's going on with that. Okay, you don't. Everybody else that says they're the same can have a test question evaluating that. Since you decided that it's not, or that it is more difficult, you don't have to worry about the amount of forces. Everybody else now has to interpret the amount of forces. Participating can be helpful. Okay, so let's try another question here. Which has the the higher melting point? Top or bottom? And Cody, if you would like to get involved, you can get involved. You don't have to step this one out. Why?
Because it has a bond of hydrogen to oxygen.
Does it have a bond of hydrogen to oxygen? So I like where you're going. You looked at the structure and you said, let's identify the bonds. Phenomenal. Okay, you're calling a hydrogen to oxygen bond. And I'm going to guess you're saying hydrogen to oxygen because of that, right?
Yeah.
Okay, how do we read our formula?
Left to right.
Left to right. So what do we start with?
Carbon.
Carbon. What needs to be connected to that carbon?
Hydrogen.
How many?
3.
Are those 3 hydrogens taken care of? Carbon's missing its octet, right? What's it need to bond to? What's the next thing in the sequence? What's the next thing the oxygen bonds to? Do I have an OH bond? No. Damn it. I like where you went. That was awesome. Unfortunately, it doesn't always work. So what are the bonds present? Hydrogen to carbon. Carbon to oxygen. Oh, you're right. That's it. Okay. Carbon to hydrogen is what type of bond? What type of bond? Non-polar covalent. What type of force? London dispersion. What type of bond is carbon to oxygen? Polar covalent. How do you know that? What's that? What was our definition for polar covalent? Everything else. So I don't quite accept that. Everything else. Why is carbon to hydrogen not? So why are we saying carbon to oxygen is polar covalent?
It's not carbon to hydrogen.
It's not carbon to hydrogen.
And it's not the same thing.
Not same to same. So it's not nonpolar covalent. I completely agree. Why is it not ionic?
It's not a metal.
Ionic is metal to nonmetal. Neither carbon nor oxygen are metals. So it can't be ionic. It can't be nonpolar covalent, which means it's whatever's left. Now it's everything else polar covalent.
Didn't you say that there was one specific bond between 2 elements that's just so incredibly common that we classify it as something that it's not?
I did not reference a bond as that, but yes, I did reference something else as that.
Yeah, it's something to do with organics. Like, so like
Anybody remember that?
hydrogen bond.
Hydrogen bonding. And you said bond. He just said hydrogen bonding. Why are you still wrong? Is hydrogen bonding a bond? No, it's a force. It's an intermolecular force. We haven't really gotten to the force yet for this compound. We're only looking at the bonds. Okay? Once we've looked at the bonds, we can interpret the forces, then we can interpret if we have hydrogen bonding. Okay? Hydrogen bonding is the last step. If we have a polar covalent bond, what type of force would we get? Dipole-dipole. If we have a dipole-dipole, what should we evaluate for? Hydrogen bonding. How do I know I have hydrogen bonding? I must have a hydrogen bound to nitrogen, oxygen, or fluorine. Do I have a hydrogen bound to oxygen, nitrogen, or fluorine in the CO bond? No, which means it's not hydrogen bonding, it's dipole-dipole. Right? What did we say our force was for the top one? That was all London dispersion. Okay? So let's go back to what Christian suggested. Of course, it's just going to be kind of the end of all this one. I apologize. Jumped out and said the bottom one has the higher melting point because of hydrogen bonding. Okay? Hydrogen bonding is a strong force, so that might suggest he was right. Do we have hydrogen bonding? No. What was the force that the bottom one has? What was the force? Dipole-dipole. Is dipole-dipole stronger than London dispersion? Yes, which means
I was right.
Christian could very well have been correct. What else do we have to take into consideration now? The amount of forces. When we look at this compound, it's a relatively tiny structure. When we look at the compound above, it's much larger. Okay? The bottom one says it's a higher melting point because it has a stronger force. The top one says it has a higher melting point because the amount of forces. Which one wins? Because everybody except Cody said that was an easy question, I do kind of expect an answer on that.
Flip a coin.
Okay? It does pretty much come down to flipping a coin. Okay? It is not an easy differentiation to make. Okay? We stick with the strongest force. If everything holds true and the strongest force doesn't allow me to differentiate, then I'll move to the amount of force. Okay? In this case, I've got the strongest force, so I would suggest the bottom one. Is the amount of force going to potentially mess with this? Yeah. I have two different things changing. So when I see a difference, what was the change due to? I don't know. Was it due to the stronger force, or was it due to the amount of force? We haven't limited the variables enough to be able to come to a valid conclusion. Okay? You can use that with virtually any system that you look at. Have you controlled all of the variables to be able to say why your conclusion is valid? In this case, we can't make a good conclusion on it. Turns out, and you might have to check me on it, I think the top one actually has the higher melting point. Okay? Why does it have a higher melting point? The amount of force became important. Okay? Well, when does the amount of force come important? Okay? We've gotten into weird arguments with Tyrannosaurus rexes and mountains and babies, so we'll switch it up a little bit. You get to fight me or a baby. Let's not do a baby, 5-year-old. Okay? Which one are you going to pick? The outcome of... What?
Depends on what day it is. I haven't decided on that one.
Jeez, you guys are way too nice. Okay, don't fight me. Fight someone like me. Okay? Versus a 2-year-old kid. The outcome of which you die if you lose. That's the end result. You either fight the 2-year-old or someone like me. If you lose, you die.
Guaranteed.
Let's not open up that can.
Kind of thing. Should say someone like you with face tattoos.
Someone like me with face tattoos, sure. Right? You would probably take on the kid, because you could probably beat up the kid. Right? You could probably still beat me up, fair enough, but I'm probably going to put up a better fight than the 2-year-old kid. At least acknowledge that.
Could you be like killing a 2-year-old child?
But the kid
That's
would
my
die.
chances of being fighting.
You don't have to kill the kid. If you lose to the kid, though, you die. So the kid can still die. Okay? So, but what happens if you now have to fight 2 kids versus someone with face tattoos? Or 3 kids? Or 4 kids? Or 5 kids? Where's that line where you're like, I think I'm going to deal with the face tattoos? 5 years old. And you can create an arbitrary line. There's now 1,000 of them, 1,000,000 of them.
4 people can attack you at once.
Where there's no limit to how much they can attack. Eventually, you could run into the situation where worst case or your best case is you're now going to collapse under the suffocation of the amount of kids buried on top of you.
They're going to die or something.
Right? There's going to be a line where you're now going to switch.
Throw a fidget spinner and they're going to go running after you.
There's going to be a line where that differentiation happens. The question becomes is where is that line? That line is going to be different for probably everybody in the room. The same kind of thing happens with chemistry. We don't hit a perfect line. Which is why when we ask questions about melting point, did we see the question comparing these 2 things? No. The questions we saw were these. And I can take you one step further. The questions you'll see will be like these. Because how do we tell a difference between these? It is going to be based solely on the strength of the force. Not amounts, just the strength of the individual force. It is that initial interpretation that is all you need to do. Right? That in and of itself is still a sequence of steps. We just walked through those steps. You have to be able to do that. Okay? So with that in mind, what else could we do? Right? What happens if we look at a phase transition? So this is just kind of a thing to think about with heat versus temperature. So I'm going to take a pot, put it on the stove. I'm not going to turn on the stove yet. And it's going to have a bunch of ice in it. Okay? So on this curve, where would I be? I want to put a red dot. Where's that red dot? So the bottom left, so somewhere in here. Have I turned on the stove? No. So am I supplying any heat? So what's my heat? 0. Okay, so I need to be somewhere all the way over here. What's my temperature going to be?
Most likely 30, minus 30. Yeah, 32 degrees. Around
32 degrees
plus.
Fahrenheit. Right? And I'm not intending to rip on you too much. What's our issue with Fahrenheit? That's not science, so fix it. So we could try 0 degrees Celsius. So that means ice only exists at 0 degrees Celsius. If I move to like -4, -5, -6, I don't have solid ice anymore.
Oh, did you say we're melting ice?
I just said I have a pot of ice.
Okay.
Okay. We could drop all the way to 0 degrees Kelvin. What do we know about 0 degrees Kelvin? Absolute 0. Have any of us gotten there? No. We've not obtained 0 degrees Kelvin. It doesn't exist as far as we're concerned. Okay. So where's our temperature going to be? At most 0 degrees Celsius. It would likely be significantly under that. Okay. If you look at most freezers actually go -4, -5 degrees Celsius. Okay. Why? What happens if we had our ice stored at 0 degrees Celsius? What does it start to do? It melts. What is the whole point of your freezer? To keep it from melting. So we drop it to lower than the freezing point to ensure that it stays a solid. So if we just take that pot of ice and somehow able to measure the temperature, let's just say we start at -5 degrees Celsius. I now start to heat it up. Okay? So I'm going to start moving along this direction. What's going to happen to the temperature? It's going to go up. I'm adding heat. That heat energy is going to make the ice now warmer. So the temperature starts to go up as well. It'll go up until what happens? Before we get to a boiling point, nope, we're still adding heat. What's that? It'll melt. Okay? When does it melt?
32 degrees Celsius.
Try again.
33.
Try again.
0 degrees Celsius.
0 degrees Celsius or 32 degrees Fahrenheit. Okay. At 0 degrees Celsius, what happens? I'm still going to add heat, so I still need to move in that direction. Does the temperature go up? So if I take ice and put it at 0 degrees Celsius and I add heat, it's all liquid. It's gradual. Does ice exist above 0 degrees Celsius?
Yes,
I've seen it before.
No, you haven't. The temperature of that slush is, guess what?
below 30.
0 degrees Celsius. Okay. What's happening is that local environment is going to stay 0 degrees Celsius. Okay. You go, oh, I saw snow and it wasn't 0 degrees Celsius outside. Take the temperature of the snow, guys. Not the temperature of the air. Take the temperature of the snow. Guess what temperature it's going to be? 0 degrees Celsius. Because when do we get solid water? 0 degrees Celsius. So as I continue to add heat, what happens to the temperature?
It's gonna
So we heard that it rises, which means at that point, what happened to all of my ice? It all instantly turned into a liquid. Does ice instantly turn into a liquid?
It'll plateau for a little bit.
As we add heat, the temperature does not change. The temperature plateaus. Until what happens? All of the ice has become liquid. Now what happens when I continue to add heat? Now the temperature can rise. Okay? What we're looking at is the phase transition from solid to liquid. Okay? And our temperature will rise again until what happens? Till it boils at what temperature? 100 degrees Celsius. Again, what happens to the temperature when we hit that point? It plateaus. When you stick a pot of water on the stove to cook spaghetti, you heat it up to boiling, then what happens? It doesn't all just go poof into the gas as soon as we hit 100 degrees Celsius. What happens? It sits there with a rolling boil. What is the rolling? It's the liquid turning into a gas. That's why it's boiling out of the solution. It's bubbling. That is literally the gas transition. You're still adding heat into it, but the temperature doesn't go up. It plateaus again. Until what happens? Until all of it has transitioned to a gas. So I'm looking at the liquid to gas transition. At this point, what happens is I continue to add heat. So gas does not get any hotter than 100 degrees Celsius. All gases cap out at 100 degrees Celsius.
Well, if we have the ice in a pot and it boils off, there's no more water in the pot.
There's no more water. That doesn't mean we haven't trapped the gas and continued to heat the gas.
Now that you say that,
What's going to happen to the temperature of the gas? It's going to continue to rise. Okay? Until what? It doesn't actually have to be that hot. It's more going to be concerned about his suggestion of trapping the gas. Harder to trap a gas. Why? The whole point of gases is that they fill the volume of the space that holds them. If we've got a pot on the stove, where's the gas going? Into the room, which is then filling the room with gas. Okay? That's why it can contain it. Right? So eventually we could heat that indefinitely upwards until we potentially hit another phase barrier, which we could. Are we concerned about more phases?
are there more phases for water?
So, interesting question. Are there more phases? Yes, there are. We have plasmas. We have different phases for solids, believe it or not. How many of you want to worry about those phases? You guys should talk to me after class. Everybody else doesn't need to worry about it. We only have 3 phases to stress about. So when you see a pipe that says caution steam, they aren't referencing steam, gaseous water at 100 degrees Celsius. They're probably referencing gaseous water at 200, 300 degrees Celsius. Stuff that would probably melt your face off when it comes in contact. That's why they're saying caution steam. Not just, oh, I'm just sticking my face in a pot of boiling water. Okay? So what we've got here is a phase diagram. If you have to move into 151, what you do is spend a lot of time talking about quantifying the amount of heat you're putting in and how much the temperature changes. Okay? Quantifying the amount of heat you have to put in to cause a solid to entirely shift to being a liquid. So you end up quantifying each of those steps. If you acknowledge that this figure exists and you understand the meaning behind this figure, all of that stuff is just quantifying this diagram. That's it. Okay? And it sounds really complicated, but it really isn't that bad. It's just quantifying those steps. Okay? So, what else could we do with our intermolecular forces? Based only on intermolecular attraction, predict which of the following liquids has the highest vapor pressure. Okay? This is probably the least favorite question for students, and probably one of my most favorite. Requires a bunch of different knowledge to be associated with this. Okay? Does any word particular jump out at you? Pressure. Pressure. Cool, I agree. So I'm glad we're on the same wavelength. Pressure. When are we looking at pressures? We're looking at pressures when we have gases. Are we looking at a gas? No. Okay? Are we looking at just a pressure? No, what are we looking at? A vapor pressure. Okay? Well, what is a vapor pressure? Pressure is a gas. What is vapor pressure? It's the pressure of the gas above a liquid. Okay? So if I have a high vapor pressure, what does that mean? Vapor pressure is the pressure of the gas above the liquid. If I have a high vapor pressure, what does that mean? I have a lot of gas. Okay? If we have a lot of gas, what does that mean about its boiling point? The highest vapor pressure is going to coordinate to a lot of gas, which means a low boiling point. Okay, because the lower the boiling point, the more likely it's going to be in what phase? The gas, which is exactly what we're saying here. High vapor pressure, a lot of gas, low boiling point. How do I get a low boiling point? Turning the heat down does not change the boiling point. That changes the temperature that you're putting into the substance. That does nothing to the boiling point. It's like saying, how do I change the color of this shirt? Close my eyes. You didn't change the color of the shirt. Okay? Bleach, we could do a chemical change. So, how do I get a low boiling point? What does that mean?
It's low forces.
Okay? There's a weak attraction between the individual molecules. Weak attraction leads to weak forces. What would be my weak force? London dispersion. Do my answers say London dispersion? Does it say London dispersion in anywhere up there? No. Okay. How do I know I have London dispersion? Because I have to be a little bit more specific on that. I agree with you. Non-polar covalent bonds. Okay. I kind of cheat and call it just covalent. Okay. Non-polar covalent doesn't say non-polar covalent, so what do I need to look for? Carbon to hydrogen and same to same. They all have carbon to hydrogen. Is it not very helpful? Go ahead and take a look at answer choice A. What do you see? Carbon, hydrogen. I completely agree with you. That was useless. Followed by carbon. That was useless. Followed by oxygen. Is oxygen carbon? Is it hydrogen? Am I getting same to same?
Yes.
I'll accept yes. Technically no. What do I have at the end? Hydrogen. I have OH. Is that a non-polar covalent bond? No. Is that my answer? No. Next one. Carbon to hydrogen. 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 Carbon to... Well, wait a second. Everything that I just erased was the non-polar covalent bond. Meaning?
So you have to take in the amount of the amount of force.
Ooh. So good step. So number one, I said, hey, that matched exactly what I wanted. But then Nick put up a point, we might have to be concerned about the amount of force. Okay? At least temporarily, though, I found an answer that matches this system. So if my answer choices were between A and B, B is my answer because it has a weaker force. Okay? So B immediately gives me a weak force, which looks good. Okay? Nick's saying we got to worry about the amount, so we'll come back to that if need be. Move to B, what do we see? Carbon to hydrogen, carbon to hydrogen. Ooh, carbon to oxygen. Is that a non-polar covalent bond? No. What does that mean? It's not right. We move to D. Carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. We have a carbon to chlorine. Is that non-polar covalent? No. What does that mean? Not my answer. Next one, carbon to hydrogen, carbon to hydrogen. Carbon to sulfur. Is that same to same or carbon to hydrogen? No, which means not my answer. So back to Nick's point, do we have to worry about the amount of the force? No. Remember what I said earlier? We should not be having to worry about the amount of force. Okay? What we're concerned about is the strongest force, or in this case, the weakest force. Okay? To process through this, all of this interpretation needs to happen. If you miss any one of those steps, you're just guessing. That's why this is a phenomenal question. Okay? Within it, you have to know vapor pressures. You have to know something about gases. What does that mean about boiling points? What does that mean about forces? What does that mean about the bonds that make them? There's so many different interpretation steps behind this that it becomes a phenomenal question at understanding the application of those forces. Okay? When it comes to the exam, that's what you're expected to do. You are not expected to regurgitate that hydrogen bonding results in a dipole-dipole force from hydrogen bonded to oxygen, nitrogen, or fluorine. That's not there. You have to be able to do these interpretations. Okay? Kind of like what we have to do for dimensional analysis. It's that same thought process and organization behind it, step by step by step. Make sense? Okay. So the next fun topic is solubility. Okay? Which we've talked about solubility before, so this shouldn't be too wildly new, at least at first. Solubility is the ability for anything to dissolve in a liquid. Okay? Gas, liquid, or solid, to dissolve in a liquid. That's solubility. Okay? If I want to get more specific and talk about the ability of a liquid to dissolve in a liquid, I can refer to miscibility. Okay? The big rule of thumb that comes out of them is this statement, like dissolves like, okay, which if you notice up there, I'm not a fan of. Like dissolves like. Like what dissolves like what? Okay. Water and pineapples. Okay, they both have water in them, so I expect pineapples to dissolve in water. Okay. I need some other context behind it. That context is the forces. So I have to be able to look at an individual compound, determine what forces are present, and then compare those forces from one compound to another compound. If those forces are similar, what does that mean? They dissolve, which would mean they were soluble. Okay, so let's take a look at the first example. I have H2O. What bonds are present in H2O? Hydrogen to oxygen. What kind of bond is that? That is not a hydrogen bond. What kind of bond is that? That is not dipole-dipole. What kind of bond is that? That is a polar covalent bond. What kind of force comes from a polar covalent bond? A dipole-dipole. If I have a dipole-dipole, what should I also consider? I should consider, is there hydrogen bonding? To decide if I have hydrogen bonding, what do I have to see? Do I have a hydrogen bonded to oxygen, nitrogen, or fluorine? Do I? Yes. This is now hydrogen bonding. Okay. It turns out that's the only intermolecular force for that compound because those are the only types of bonds. When we move to the next compound, What bonds are present? I'll accept that, but I want specifics first. Carbon to hydrogen, and here's where I'll throw in Cody's suggestion, nonpolar covalent. What else is present? Carbon to oxygen. What else is present? Oxygen to hydrogen and carbon to carbon. What kind of bond between oxygen and hydrogen? Polar covalent. What kind of bond between carbon and oxygen? Polar covalent. What kind of force comes from a nonpolar covalent bond? London dispersion force. What kind of force comes from a polar covalent bond? What kind of force comes from a polar covalent bond? What kind of force comes from a nonpolar covalent bond? I have some London or some dipole-dipoles. Should this dipole-dipole be hydrogen bonding? Yes, I have a hydrogen bound to oxygen, nitrogen, or fluorine, so I have hydrogen bonding. How about the next one? Should that one be hydrogen bonding? No. Which of those forces is going to be the most important for me to evaluate for that molecule? Hydrogen bonding. Why? I don't accept that. I know where you're going, but I don't want that yet. It is the strongest force in that compound. So now I can compare the strongest force in each compound, and what is it? Hydrogen bonding to hydrogen bonding. Are those similar forces? Yes. So what do we know? We know water and ethanol mix. Welcome to spring break. Water and propane. Should those mix? How do we decide that? Well, water, let's not walk through all that one again. We got hydrogen bonding, right? What is the force in propane? What are the bonds? Carbon to carbon, carbon to hydrogen. What kind of bond is carbon to hydrogen? What kind of bond is carbon to hydrogen? Non-polar covalent. Did you say the non the first time? Okay. Carbon to carbon. Non-polar covalent. What kind of force comes from a non-polar covalent bond? Which is the strongest force? London dispersion. London dispersion in comparison to hydrogen bonding. Are those similar? No. What does that mean? They don't mix. Because these are both under the liquid rule, we would reference these as immiscible. That im means not mixing or not dissolving. Okay? With solubility, just like with our melting points, we're looking at our strongest force and making that comparison. We will not worry about the amounts of forces. In fact, I won't even show an example. Okay? The amount of force does come into play, just it won't come into play in this class. It becomes much more important later on. What about ionic compounds? What is the strongest force in sodium chloride? What about ionic compounds? What is the strongest force in sodium chloride? Okay, so we could go with electrostatic. That works. That's the hard word. Or ionic. It's an ionic force. So ionic versus hydrogen bonding. Are those similar? They're both strong. Almost. What's similar enough? I don't really know. Sometimes it works out where they're really nice and they're perfect. Sometimes they're not. Okay? So when it comes to questions, you could see questions like, which one of these is most soluble? Okay? So you're looking for the two forces that are closest to each other. Okay? Typically the questions you're going to see are black and white. They're the same force in each compound. Okay? Should we be using ionic compounds at all with this rule system? Okay? Shake of the head, no, I agree with you. Why?
Is there metals? Yeah, this is asking for, actually, yeah.
This doesn't explicitly state one way or another that we should be looking at metals or nonmetals and nonmetals. Liquids works for miscibility. It doesn't work for solubility. Solubility is anything to dissolve in a liquid. Okay, so I could reference solubility and I still shouldn't be using these. What would classify the ability for this compound to dissolve in water? Should I be looking at the intermolecular forces? No.
Solubility
Good answer.
rules.
I should be using the solubility rules. The solubility rules that apply from double replacement reactions back in Unit 2. Okay? Are you going to be responsible for memorizing some solubility rules? Yes. Okay? The exact details of which solubility rules you will need to memorize, I will post online. Okay? But the final does expect you to memorize some of them. Why? I don't know. I think it's dumb. But that's the expectation. Okay? If you're curious about that, the final exam review should be online. Did anybody actually look for it? Is it there? There is also a final exam memory thing. I think it says FE, Mike's Memory or something like that. Okay? That is all the stuff that you should be memorizing for the final. Okay? The big things. Okay? There are some small things, like I don't list every single element that you're supposed to know names of. Okay? But those are kind of the larger subheading stuff. Okay? They include some solubility rules. Okay? We can still look to see why salts would dissolve. So we'll look at this one really quickly. If I took a look at table salt, why would it dissolve in water? Well, remember when we talked about water, it had a polarity. The oxygen was partially negative and the hydrogen was partially positive. Why? There's a large difference in electronegativity between the oxygen and the hydrogen. Oxygen sucks the electrons away from the hydrogen, giving us a large partial positive on the hydrogen. When we look at salt dissolving in water, which of the ions, sodium or chloride, would we expect to interact with that positive hydrogen?
Sodium.
So we hear a suggestion for sodium. What is the charge on sodium? Is this orange interaction look good to you? No, why not? That is positive to positive, and that is bad. So what ion should interact with the hydrogens? The chloride. Okay, why? Whoops, gotta fix that too. The chloride is negative. So we get the negative to positive, that starts to cancel some of the charge on the hydrogen and cancel some of the charge on the chloride. Okay? That would mean chloride would dissolve. But remember, where is this coming from? This is coming from sodium bound to that chloride. What connects the sodium to the chloride? An ionic what? An ionic bond. What is connecting the chloride to the hydrogen? Try to avoid getting specific. It's going to be a force. Which is stronger? The bond. Why would the bond break to form a weaker interaction?
Because it's
Okay. So one option is we know it happens, so we just say it does. Okay. What are you suggesting?
There's the sodium's gonna go to the hydrogen.
So the sodium could go to the oxygen, but then we'd still just be looking at the other end of that. There's another argument for why that chloride should interact with water.
I don't know if I'm going where you want me to go, but sodium is group 1 metal. And then
No,
solubility.
unfortunately not. When we go into solution, does water only show an interaction on one side of the chloride? No. It'll actually show it on 6 sides. Which means I get 6 weaker forces, but those 6 individually weaker forces in sum total are stronger than the one bond. That's why it dissolves. So we can quantify that. If you move into 151, you do. Okay, they do actually ask you to quantify those interactions. I think it's a bit silly because it's just this is this number, this is this number. Add and subtract to prove that it happens. I can add and subtract random numbers also. It doesn't have any effect. The biggest point here is that you're forming a more stable interaction by having more interactions. The amount matters. Okay? So let's switch back to the easy one for another example. Apply the like dissolves like rule to predict which of the following liquids is miscible with water. Like what? So we're talking about forces. Okay, the forces on what things? How many things? As an example, I wrote forces how many times? Twice, because I'm looking at the forces between two things. So I need to compare two things. Yes, there's 5 answer choices, but only one of them is correct, meaning that is the one thing in our answer choice. Where's the other one? Water. Why did we not write the formula for water? Because the most common mistake that students make when they look at this question is like, I can't answer it because I'm only given one substance in my answer choice. You're given the second in the question, it's water. If we'd written out the formula, sometimes that's enough to trigger you to go, oh, I'm now comparing water to something else. What is the force in water? Hydrogen bonding. So if I'm trying to look at my rules, this says apply like dissolves like to predict which of the following liquids is miscible, meaning it dissolves, which means the answer I'm looking for needs to have hydrogen bonding. How do I know I have hydrogen bonding? Okay. Not necessarily oxygen and hydrogen. Okay. I need to be looking for a hydrogen bonded to fluorine, oxygen, or nitrogen. Okay. Because that's specific to this question. So one of the big problems, you go, oh, I need to find the one that's hydrogen bonding. I would argue we shouldn't be jumping hydrogen bonding to hydrogen, fluorine, or oxygen. We should be looking for a polar covalent bond. A polar covalent bond that also has hydrogen bonded to nitrogen, oxygen, fluorine. By going from the bond to the force, we can then better apply our rules to more systems instead of just answering the one question. Key off of the bond to force relationship. That relationship is critical to solving. So we go through and look at our questions, our answer choices. This gets extra irritating because the things that they gave us here are not structural formulas. They're just formulas. What are the bonds going to be present in C5H12? Carbon to hydrogen, carbon to carbon, which would all be nonpolar covalent, which would be London dispersion force. Is that correct? No. Remember, my target was hydrogen bonding. The next one. London dispersion force. The next one. A carbon to chlorine, which would mean what kind of bond? For it to be ionic, what do we need to have? A metal. Is carbon a metal? Is hydrogen a metal? Is chlorine a metal? No. So it is not ionic. What is it? It is polar covalent. Polar covalent bond means dipole-dipole. Oh, accidentally, you were only given these 3. Which of these 3 is the answer? Why is C now the answer? Dipole-dipole is the closest to hydrogen bonding given those choices. Make sense? If we continue through with the rest of our answer choices, the next one, we have an OH, which is polar covalent, dipole-dipole, hydrogen bonded to oxygen. That's hydrogen bonding. D becomes our answer. Toluene, we look at toluene, it's going to be still London dispersion force. Make sense? So again, applying the forces all the way through, all the way through. Okay? You got enough with forces? Cool. We'll switch topics. Acids and bases. It's like I knew that was going to happen. I didn't. I just made it up. Acids and bases. We look at those compounds. Is there any one of those that jumps out of the page at you as like, I should be careful with that? Why the aqueous one? Don't quite accept that. Aqueous does not mean acid, because if I give you sodium chloride aqueous, that is aqueous. That means when I cry, my face literally falls off because of all the acid issuing out of my eyeballs. It may feel like that, but that's not the case. It's a combination of the hydrogen in front and the aqueous in back. So that one gets called an acid. The other ones we wouldn't name as an acid, at least at this stage. Right? Why do we have a special nomenclature system for acids? Because acids are dangerous. Historically, we've recognized the danger behind them. Okay? So observationalists, so people that were just playing around with stuff, noted some weird things. Right? Noted when we took some compounds, they tasted sour. Right? And they were sticky feeling. Those happen to correlate to acids. Right? And you might say, someone took some acid and started tasting it. Welcome to the 70s. Yes. Right? You could also look at probably the death of lots and lots of people with someone being like, I've got this weird vat of stuff. What happened? I'm not going to stick my hand in it. Hey, slave, come here. Oh, wow, that took off all your skin. I'm sorry. We're gonna put a label on that so nobody else does that. Oh, I got this other vat over here. It looks the same, but it's not the same. Hey, slave, take it. Oh, shoot. Sorry, I took all the skin off your hand again. Okay, well, it did the same thing, so I'm going to mix them. Here, because they were both dangerous, I know, slave, I just melted both of your hands off, but here, mix them for me. Mix. Poof, explosion, burning acid, boiling water everywhere. Oh, I just killed the dude. Damn. We should make sure we put labels on that to make sure that we know not to mix those, because that was a bad idea. Okay? Science. Okay? Acids get labeled as corrosive. The bitter tasting, slippery feeling comes from bases, which get labeled as caustic. Look up the definition between corrosive and caustic, and guess what? It's the same thing. Why do we have two words meaning different things, or meaning the same thing, and not just because it's the English language? One is for acids and one is for bases. Why? So that when someone looks at a bottle and it says caustic on it, and someone looks at another bottle and it says corrosive, they go, I'm going to keep those separated from each other. Because what happens when I mix them? A violent exothermic reaction that could cause lots of bad things to happen. So we changed the labeling system to help us acknowledge to keep them separate. Acids classically have a sour taste. They do have a sticky feeling. Why a sticky feeling?
Because your skin's melting off.
Your skin is melting. Okay? Not a lot, but a little bit. Bases are bitter tasting. Okay? Have you ever had your mouth washed out with soap? Guess what soap is?
Base.
A base. Okay? They're also slippery feeling. Why are they slippery feeling? Because your skin is melting. It's actually reacting with the base to form soap on your skin. Your skin cell walls are actually melting to form soap. Okay? Yeah, pretty awesome. Okay? At the highest level of concentrations. Okay? So those are the big kind of observations of those. Because we acknowledge that those were insanely dangerous things, we defined them, we named them, so that we could reference these and share that information with other people so that they didn't get hurt in the same ways. Okay? That's why we have acids and bases. These are classically the oldest form of chemistry, and so they get those extra names, and they get studied a lot. That is virtually all we do in Gen Chem, is look at acids and bases. Okay? So, yeah, we'll look at it. What kind of reaction is this? It's a neutralization. We know it's a neutralization because Mike screwed up and left off the phase. That first one is an acid. Right? If I have an acid, more than likely, what am I reacting it with? A base. Acids and bases react with each other in a neutralization reaction to produce water and a salt. Okay? That is our definition for neutralization reactions in this course. Okay? So that works. That's nice. Okay? We want to expand that definition a little bit because we just said, well, when we mix them, we create neutral stuff. So it's okay. After the guy died and dissolved away into nothingness, all the liquid that was there, that didn't really hurt me anymore. Okay? So they were neutralized. Okay? I want to come up with a better definition. The first definition came about from a guy by the name of Arrhenius. Right? He noted that when we had acids in water, that the hydrogen ion concentration went up. Right? Why would the hydrogen ion concentration go up? If I put HCl into water, what happens to that bond? It breaks to give me hydrogen ion and chloride. After a sequence of enough experiments, we noted that hydrogen ion was the dangerous one. So when we came up with a definition, we referenced our definition according to the hydrogen ion. How do I know it's hydrogen ion that's dangerous and not the chloride? Because we cried. And when we cried, we noted that we didn't get the same effect as pouring acid on my face. It's a different relationship. Okay? So the hydrogen ion is the dangerous one, so there's our definition. He also went through and did the same thing with bases and noted that the dangerous one is the hydroxide. Okay? So we established those two definitions. Okay? Acids increase hydrogen ion, bases increase hydroxide ion. Okay? This is a bit overstated, but not quite. These definitions are very, very narrow, and they really only have solid meaning in general chemistry. Okay? So someone had to come through and refine these definitions and make them a little better. Okay? So in that overstated, because it started to look like people were now scratching stuff out and erasing things, you are still responsible for these definitions. Okay? You need to know these. Okay? The question just becomes, it's a limited usage in the broader sense of chemistry and broader sense of reactions. Okay? So the second definition came from two guys by the last name of Bronsted, last name of Lowry, okay? And noted that some species would act like Arrhenius, but not necessarily forming hydroxide. Okay? So what they did was expanded the definition by only focusing on the acid part of it. So the acid part was H+. Okay? So if we look at the top reaction, let's ignore the top reaction sort of. If we add HCl to water, let's just do HCl. We get H+ and chloride. If I did the same thing with some other species, I don't see the formation of hydroxide. Okay? So in this system here, there's no water. Well, if there's no water, then Arrhenius' definition is invalid. Okay? So Bronsted and Lowry shifted the definition base to get rid of water as a basis for the entire definition. So when we look at the reaction shown below, HCl still gets rid of H+. But does that next species have hydroxide? No. So I can't call that a base. And yet I have an acid. And acids react with bases. So what did the base do? What did this blue species do to become like one of the products? So when you look at NaNH2, which of those products looks most like it? Okay. So we hear an argument that NaCl looks most like this. So this species here has how many things in it? So I see 1, 2, 3, 4 things. Okay, and we look at NaCl, it has one of those pieces, right? Versus NH3 that has three of those pieces, what looks most similar to NaNH2 on the other side of the equation? NH3. What happened to make NH3, to go from here to here? Gained a hydrogen. Okay? So our acid donated a hydrogen, or lost a hydrogen. Our base gained a hydrogen. Okay. We rephrased that a little bit to get hydrogen ion donors, which are our acids, and hydrogen ion acceptors, which are our bases. So the definition is centered on the hydrogen ion. This definition also has some massive flaws behind it, but it's broad enough that it encompasses a lot more reactions than the Arrhenius definition did. Okay? So the Bronsted-Lowry definition, for those of you that have to move up into OChem, that's one of the common reactions, and you will have to classify compounds as Bronsted-Lowry acids and bases just by looking at their structure. Okay? The next kind of, never mind, we're out of time. So we'll just start with that. We'll pick up with our conjugates on Tuesday.